How's it going, everybody? Today, what we're going to be talking about is determining chemical formulas. We're first going to go through how to figure out an empirical formula, and then after that, we're going to learn how to do molecular formulas. Okay, so to get things started, we're going to be talking about empirical formulas, and they're the compounds in the formula with the smallest whole number mole ratios of the different atoms in the compound. So you can kind of see some examples down below. We have NaCl, sodium chloride, which is the lowest form that NaCl can be in. We have H2O and MgCl. Again, all those are just the smallest chemical formula that those compounds can be in. So to determine the empirical formula, you got to follow these 5 steps. The first thing you're going to do is you've got to figure out the number of grams of each element in the problem. Remember that if we are given in percents always equal up to 100%. So if it's like 55%, we can just say it's 55 grams. After we do that, we're going to convert each mass to moles from the periodic table. After we do that, we're going to divide each mole value by the smallest calculated moles. All right, step 4 is we're going to round to the nearest whole number. Now, hopefully most of these problems, when you solve it out, if there is a decimal, it's only a couple off, where it's easily to round to the nearest whole number. However, sometimes it's too far to round, and you're going to have to multiply by some number to get to the smallest whole number. So looking at the steps here below, it says if the number ends in the following decimals, follow the rule below. So if we end in 0.20, we're going to multiply it by 5. If the number ends in 0.25 or 0.75, we're going to multiply it by 4. If it ends in 0.33 or 0.67, we're going to have to multiply it by 3. And if it ends in 0.5, we're going to multiply it by 2. Now this here is a very crucial piece when figuring out the empirical formula. So it's important that you kind of take note. Obviously, I put a little star by it, but make kind of note in your head. You might want to write that down in your own notes. But again, when we divide by the smallest number of moles, if we get any of those decimals, we're going to have to multiply it by the correlating number. All right, and remember, we need whole numbers for the empirical formula. So let's take a look at some examples. All right, so let's look at example 1 here. It says an analysis of a 20-gram compound containing only calcium and bromine indicates that 4 grams of calcium are present. What is the empirical formula of the compound? Okay, so step 1, we've got to figure out how much grams of each thing we have. Well, if we have 4 grams of calcium, that means that we have 16 grams of bromine. Now that we know how many grams of each thing we have, we're going to divide each by its molar mass. So we're going to have our periodic table out, and we're going to go ahead, and we see that we have 4 grams of calcium. The molar mass of calcium is 40.08, and remember, I just pulled that off of the periodic table, so divide it out to give us the number of moles. We're going to do the same thing for the bromine. So 16 grams of bromine divided by 70.90, which is the molar mass of bromine, and we get 0.2002. Now remember, the 4 grams of the calcium was in the problem, and the 16 grams of bromine came from 20 minus 4. All right, so the next step that we're going to do is we're going to divide by the smallest number of moles. Well, the smallest number of moles here is the calcium. Okay, 0.0998 is smaller than 0.2. So what we're going to do is we're going to divide each mole by the smallest number of moles. Okay. So here we go, we take 0.0998 divided by itself, we get 1. Then we're going to do the same thing. We have 0.2002, and we're going to divide it by the smallest number of moles, which was the calcium, 0.0998. When I did that, you can see that I got 2.006. Now, again, that's not one of those decimals that we talked about earlier, so I can simply just go ahead and round that to the nearest whole number. All right, so what do these two numbers mean? Okay, that tells us that we have 1 calcium and 2 bromine. So all we have to do is simply write that in our formula, and I got CaBr2. Now remember that this 1 that we got right here, and I know you can't see the highlighter, but that 1 right there goes to the calcium, and this 2 comes to the number of bromine, okay? And that's how I got those 2 parts right there. All right, so in example number 2 here, it says find the empirical formula of a compound found to contain 26.56% potassium, 35.41% chromium, and the remainder is oxygen. All right, so the first thing I have to do is figure out how many grams of each one of those is. Now remember, I said at the beginning here in step 1, if we have percents, we can treat them like we go up to 100%. So the 26.56 is going to be grams of potassium. The 35.41 is grams of chromium. So the rest is going to be the oxygen. So what I'm going to do first, 26.56 plus 35.41, that's plus oxygen, it's going to equal 100. So I'm going to subtract those things together, or subtract the 2 numbers that I added together from 100, and I got oxygen to equal 38.03 grams. Okay, so now that I have the mass of each one of these things, just like last time, all I'm going to do is I am going to divide out by the molar mass of each one of those things. So here I go. All right, so you can see that I divided each mass by its molar mass, and now I have the number of moles, okay, for each one of those. So the third step here says to divide by the smallest number of moles. Well, right now, if I look at these things, the smallest number of moles that I see is the potassium. So I'm going to go ahead and set each one up. So the first thing I'm going to do is divide by the potassium by itself, and I get 1. I'm going to divide the chromium by 0.69, and it comes out to about 1 as well. It might be slightly different, but about 1. And the third thing I'm going to do is I'm going to divide the moles of oxygen by the 0.679. Now, here we go. We notice that we come out to 3.5 here. All right, and that comes out to one of those percentages, or those decimals that is too far to round, like we talked about before. So what we're going to have to do is think back and look at that chart and say, okay, I end in 0.5. So because I end in 0.5 here, what I'm going to have to do is I'm going to have to multiply each one of those things by 2 in order to get our nearest whole number. So I'm going to take that top one, the potassium, I'm going to multiply it by 2, and obviously 1 times 2 is 2. I'm going to do the same thing for the chromium, and 1 times 2 is 2. Then the last one, I'm going to take that oxygen, 3.5, multiply it by 2, and I get 7. Okay? And just like last time, these numbers that I get correlate to how many of each atom I have. So again, the 2 from the from the potassium gives me 2. The 2 from the chromium gives me 2. And then the 7 that I got gives me 7 for the oxygen. All right, here's example number 3. We have NutraSweet, which is 57.14% carbon, 6.16% hydrogen, 9.52% nitrogen, and 27.18% oxygen. So what we're going to do is we're going to calculate the empirical formula for NutraSweet. Now remember, all those percents should equal up to 100%, so we can just say that they're the same thing as the mass in grams. So again, I now have my grams, and what I'm going to do here is I'm going to divide each by its molar mass to give me the number of moles. Okay, so there's carbon, there's hydrogen, there's nitrogen, and last we have oxygen. So now I have the number of moles of each one of those things. So step number 3 here is to divide by the smallest number of moles, and you can tell that our smallest number of moles in this example is our nitrogen. Okay, so I'm going to divide each of those moles by the number of nitrogen. So I'm going to go ahead and do that. There's ours for carbon. There it is for hydrogen. Again, right here you can see that we're at 8.97, and that's close enough to round up to a whole number. So that's why I rounded it to 9. Again, obviously you do it by yourself, you get 1. And the last one I did oxygen. And again, notice here that I ended up with 2.5. Because I end up with 0.5, I got to multiply everything by 2. So I'm going to take my 7, multiply it by 2, I get 14. My 9 times 2, I get 18. 1 times 2, I get 2. And 2.5 times 2, and I get 5. So again, when I put all those together in our formula down here at the bottom, we can see that the final number I got was C14H18N2O5. So here in example 4, this one's going to be a little bit different than what we've been doing so far. Not really same concept and everything, except for this time we have a hydrate. So it says find the empirical formula of a hydrate that is 48.8% MgSO4 and 51.2% H2O. So just like we saw before, the 48.8% is going to get changed to grams, and so is the 51.2%. So we're going to go ahead and do that. And then, of course, you're going to keep these ones together this time. So you're going to keep the MgSO4 together, and you're going to keep the H2O together. So I'm going to give you guys about a minute or two to go ahead and try to solve this one on your own, and we'll check back here in a minute. All right, so like I said here, what we're going to do is we're going to divide each of those masses by their molar mass. So the 48.8 grams of MgSO4 divided by its molar mass, which was 120.38, and we got 0.405 moles of MgSO4. We're going to do the same thing with the water, the 51.2 grams of H2O divided by its molar mass, which is 18.02, and we got 2.84 moles of H2O. All right, so just like we did before, we're going to divide by the smallest number of moles, which is the MgSO4. All right, obviously, divide by itself, you get 1. And divide by the water, we get 7. Now, this one's going to work a little bit different. Everything else we so far put up subscripts for the things. However, because we're dealing with a hydrate, the 1 just tells us that we have 1 molecule of MgSO4, and that we're going to have 7 H2Os. So again, in this example, that 7 that we got goes as that coefficient for H2O. All right, this is a little bit different because we're dealing with a hydrate and we're dealing with 2 compounds, whereas everything else we were dealing with individual elements itself. So this time we're dealing with compounds. So because we were doing that, we were going to play them as coefficients. Now, a little trick with the hydrate ones when we're looking for the empirical formula, The only number that should change should be the number of waters attached to it. That the anhydrous compound, the salt in the beginning, should always be 1. Okay, so the second half of our notes, we're going to calculate the molecular formula. This is a little bit different. We're going to need the empirical formula in order to calculate molecular formula. So let's go ahead and check it out. All right, so in this slide, we're going to learn how to calculate the molecular formula. So it says, remember that the empirical formula contains the smallest whole number ratio of atoms in the chemical compound. So the molecular formula is the actual formula of a molecular compound. The molecular formula of a compound shows how many atoms of each element are present in a molecule of a compound. So it says the molecular formula is just a multiple of the empirical formula. So again, the molecular formula here is before we reduce the compound, okay, into the smallest whole number ratio. So here are some examples. Over there on the left, we're going to see the molecular formula, and I'm going to show you what changes when we have the empirical formula. So in our first example here, we have C6H12O6. They're all divisible by 6, so when we reduce it, we should get CH2O. For SO3, there's nothing we can divide here, so we actually notice the molecular formula and the empirical formula are the same number, and that happens from time to time, so just kind of pay attention to it. The next one, we have Ag2C4H4O6. They're all divisible by the number 2, and when we divide it by 2, we get AgC2H2O3. And the last one, we have C7H3O2. Now, there's nothing that we can divide them all equally by because you can't have decimals or fractions of our subscripts. So again, here's another example where the molecular formula and the empirical are the same. So again, when you're trying to figure out the molecular formula based off an empirical or empirical based off molecular, the key to remember is you have to be able to divide everything in the compound by the same thing. Okay, have to be able to divide everything in the compound by the same thing. You can't divide one by 2 and the other one's not. So when calculating the molecular formula, we got to follow some steps here. It says the relationship between a compound's empirical formula and its molecular formula can be written as follows. So this right here where it says X empirical formula equals the molecular formula, this is kind of an equation that you guys should make note of, write down somewhere. And basically what's going to happen is whatever we solve for X, it's going to multiply by the empirical formula, but it's going to multiply by its subscripts. So the number represented by the X is the whole number multiple indicated by the factor, which is the subscripts in the empirical formula, must be multiplied to obtain the molecular formula. So again, the value of X can be any number including 1. So whatever X is we're going to multiply it by the subscripts that we get for the empirical formula. So to find the molecular formula here of a substance, we must know the empirical formula. The empirical formula is molar mass, and the molecular formula is molar mass. That last one, the molecular formula is molar mass, I have to give to you. So when we see these problems, if you read something in there that says the molecular mass or the molar mass of this compound is, that's the molecular formula's molar mass. So here are the steps to calculate the molecular formula. The first thing we're going to have to do is make sure we have the empirical formula. If that's not given, then just like we did in the previous slides, we're going to have to solve for it. And all you do, remember, is to take the mass of whatever's in the problem, divide it by its molar mass, and then you divide out by the lowest number of moles. All right, once you get those the empirical formula, step 2, you just got to get its molar mass. Now, step 3 says solve for X. And I didn't write it down, but just so we're aware, when I solve for X, X is going to equal the molecular mass, divide that by the empirical, I'm just going to put M for molar mass. All right, I didn't write that down, but that's what you're going to do. And then you're going to multiply the empirical formula subscripts by the value of x, and then of course write the correct formula. Okay, so let's go ahead and solve for a problem. So it says determine the molecular formula of a compound with an empirical formula of CH and a molecular mass of 78.118, or sorry, 110. So in this problem, I've given you the empirical formula, and I've also given you the molecular mass. All right, so the first thing we're going to have to do is find the molar mass of CH, and very simply, C is 12.01, H is 1.01, so add them together, and you get 13.02. All right, so what numbers that I have right here, this 78 right here at the top, that just comes from the problem. And again, that's molecular mass. This 13.02 is the molar mass of CH. Okay, and that's where I did. So again, I solve and I get x, which is 6. Now what I'm going to do is, we saw in that formula before, x times the empirical formula. So 6 times C times H. So that's 6 times 1 times 1. So we get C6, H6. And this down here, the C6H6, is the molecular formula. So in example 2 here, it says a compound with a molar mass of 42.08 grams per mole is found to be 85.64% carbon and 14.3% hydrogen by mass. Find its molecular formula. So I'm going to let you guys solve this one. This one, again, is going to take a couple extra steps because I do not give you an empirical formula, but as always, I do give you this number up here, the 42.08, which is the molecular mass, all right, the molecular mass of the molecular formula. All right, so what you're going to have to do is you're first going to have to figure out the empirical formula. Then once you do that, get the molar mass of that, and then you're going to divide that 42.08 by that molar mass. So I'm going to give you guys a couple minutes to go ahead and solve that one. All right, so let's take a look here. Like I said, the first thing you're going to have to do is solve for the empirical formula. So you're going to take the 85.64 grams of carbon divided by its molar mass, and the 14.36 grams of hydrogen, and divide it by its molar mass. Okay? So when I do that, those are the two numbers I get for the number of moles. Now, the second step for the empirical formula is to divide by the smallest number of moles, which is carbon. All right, and when I do that, I get a ratio of 1 and 2. So the empirical formula that I got was CH2. Now remember, this isn't what I'm looking for. I'm looking for the molecular formula. But I had to solve for the empirical formula first because I didn't give it to you. So the next thing we're going to do is we're going to take the molar mass of the empirical formula, which is 14.03. So remember, this top number comes from the problem up here. The bottom number, the 14.03, is the molar mass of the CH2. All right, when I divide out here, the number I got was 2.99, so it's close enough I can round to 3. So the next thing to do is take 3, and I'm going to multiply it by the CH2, so 3 times 1 for carbon and 2 for the H. And you see that I get the molecular formula of C3H6. All right, so in example 3, I'm going to let you guys do this one on your own again. So it says we found the empirical formula of NutraSweet to be C14H18N2O5. Remember, we did that at the very beginning of the slide here, and I think problem number 3 in the first part. The molecular mass of the NutraSweet is 294.30. What's the molecular formula? Well, you already have the empirical formula. So what you're going to have to do is you're going to have to solve for its molar mass and then divide the molecular mass divided by the empirical's molar mass. So I'll give you guys a second so you guys can go ahead and do that. All right, so for this one, what we're going to have to do, like I said, is we're going to first figure out the molar mass of our empirical formula. So remember the first part here, this 12.01 that comes from the carbon, the 1.01 comes from the 18 hydrogens, the 14.01 comes from the nitrogens, and the 16 comes from the oxygen. So add it up. When I do this, you can see that I get the empirical formula to be 294.34. So looking at this, you'll notice that the empirical and molecular formula is the same. So very simply, take your molecular one, divide it by your empirical, and you get the number 1. So very simply, I just have to multiply it by 1. And in this case, our empirical and our molecular formula is the exact same. That's all I have for you on the empirical and molecular formula. Make sure you take the time to go back and do the practice examples on your own just to make sure you know what you're doing.